Unit 2, Part 3. So in this unit, we're going to start by talking about temperature and heat. So temperature is measured the average kinetic energy of the particles in a sample of matter. What does that actually mean? That means that it's really a measure of how quickly the molecules are moving in a sample of matter. And then heat or heat energy, and I meant to make a space in here, but heat or heat or heat energy can be thought of as thermal energy. Heat always flows from matter of higher temperature to matter of lower temperature. It never goes the opposite way. So actually, when during the summer, during the winter, you open a door and someone says you're letting the cold in, that's actually not correct. You're actually letting heat out of the house because heat always moves from higher temperature to lower temperature. Now, there's different scales that we can use to measure temperature. The Celsius scale is one that we're probably all familiar with, and this was developed by a Swedish astronomer, Anders Celsius. And we use if we use degrees, so if we say 0 degrees Celsius, so the degrees is the scale for temperatures, and so 0 degrees Celsius is the freezing point of water. 100 degrees Celsius is the boiling point of water. And I should say that that's at sea level, because of the pressure changes, the boiling point of water will change. Kelvin is the other scale. So it's a unit of measure on the Kelvin scale, which is a fundamental SI unit for temperature. It was developed by William Thomas, Lord Kelvin. So when we talk about Kelvin, we don't say degrees Kelvin, we just say Kelvin. So water freezes at 273.15 Kelvin. And water boils at 373.15 Kelvin. And again, at sea level, because if you change the pressure, air pressure, that will change the temperature at which water boils. So how do we make a conversion? So if I want to convert between Celsius and Kelvin, right? Temperature in Kelvin equals temperature in degrees Celsius by adding 273.15. So if I have 100 degrees Celsius and I want to convert it to Kelvin, what I would do is add 273. So I'm going to take 100, add 273.15, and that's going to equal the temperature in Kelvin. So it'd be 373.15 Kelvin. I know it's hard to see my 5 there, 1.5. All right, units of heat. All right, temperature is talking about the average kinetic energy. Heat is talking about thermal energy. So the joule is the unit that we'll use to measure heat or thermal energy. And it's a derived unit. So let's take a look at, so joule equals force times length. And I'm not going to ask you this on a test. Right? This is just background information. You may remember if you took physics in high school or if you take in college, you would see this. So force times length. So it's really, joules is, if you want to think of it this way, if I push a box, the further I push the box, the more joules it will be. If I increase the force, even though the distance is the same, then I'll increase the joules. Calorie is an older unit that's used to measure heat. It's defined as the quantity of heat required to raise the temperature of 1 gram of water, right, from 14.5 up to 15.5 degrees Celsius. In other words, by 1 degree Celsius. It's also defined as 4.184 joules. So when you've heard the calorie, But when you are talking about calories in foods, it's actually the kilocalorie. So the kilocalorie is 1,000 calories. So when we talk about food, we're talking about the capital C. So if I buy a candy bar and it says it's 250 calories, we'll say C, that's actually kilocalories. So 250 calories on your candy bar is actually 250,000 small calories. So we know that a calorie will raise the temperature of 1 gram of water by 1 degree Celsius. So when you look at a candy bar and it says 200 calories, how much would it raise the temperature? So it will raise 250. Well, let's make it easy. If you had 250 grams of water, it could raise the temperature by 1,000 degrees Celsius. Okay? So heat capacity is defined as the amount of heat energy needed to raise the temperature of a given sample of matter by 1 degree Celsius. So not all materials require the same amount of thermal energy to raise the temperature. What do I mean by that? Well, air, which is a gas, it takes less energy to raise it by 1 degree Celsius than, let's say, water. So it will take fewer joules of energy to raise the temperature for air than water. And specific heat is defined as the amount of heat energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. And if you notice over here, we're talking about 1 gram. Okay. Specific heat values can be given in joules or calories. So joules per gram degree Celsius. So that this is our formula for joules per gram degree Celsius. And what I did is I took this and I wrote it. I took this and I wrote it down here. So it might actually be easier to see it written that way. We also can say calories over grams degrees Celsius. So this one here. And we can rearrange this formula to solve for any one of the three factors. So calories, grams, or degrees Celsius. Now this degrees Celsius here, that's referring to the change. All right, so a change in temperature. And if you look over here, we can define the change in temperature as delta T. So delta T, right? Delta means change. So T is for temperature. So delta, change in temperature. And we can use this formula here to determine the change in temperature. TF, so you have TF. The F means final, so temperature final minus temperature I, which is temperature initial. This will give you the change. Okay, the change in temperature. The So let's look at a couple of examples. Okay, you have a piece of glass with a mass of 4 grams. Right, so it's 4 grams, and it's heated from 0, that should be 0 degrees Celsius, up to 41, up to 41 degrees Celsius. And it absorbs 32 joules. What is the specific heat of the glass? So remember, you have this. These are the equations for specific heat. All right. What I'm going to do is I'm going to let's take this. I'm going to use this space over here to solve it. Okay. So we have to figure out: are we using joules degree, joules per gram Celsius, or we're going to use calories. So here, because they're using joules, we're going to be using the unit joules. So if we look at our equation, C, which is the temperature change, equals, so we want to find the amount of heat lost or gained. Oh, sorry, we want to use the amount of heat lost or gained, which was 32 joules. The mass in grams, which is this right here. Delta T is the temperature change in degrees Celsius. So that's what we have right here. So you have 32 joules. Let me. So we have C. So that's specific heat. The amount of energy that we said we added was 32 joules. So I wrote that here. And the mass of our object is 4 grams. So I wrote that over here. And then the temperature change, delta T. I'm going to write that over here. So delta T equals, we said that you went from 0 degrees Celsius to 41 degrees Celsius. So 41 degrees Celsius minus 0 degrees Celsius is 41 degrees Celsius. So that's our delta T, is 41 degrees Celsius. Okay? So we're going to take 4 times 41, and that's going to be, so 4 times 4 is 16, times 4 is 164. So I'm going to erase this down here so we can see it. So I'm going to erase this. Okay. So we have C equals 32 joules. And we said 4 times 41 is 4 times 4 is 16, 4, so 164. 164. And now we're not losing our units. Nothing cancels out. So we have grams. I put a little thing here saying times degrees Celsius. And then we're going to divide 32 by 164. Let's see if my math is correct. Okay. So 32 divided by 164, and it comes out to 0. So C equals 0.195. And we have 2 significant digits, so I'm going to go to 2 significant digits. So I'm going to round this up to 0.20. Now our units, none of our units canceled out. So it's going to be joules per gram degrees Celsius. So what this is actually saying, if you look at the problem, is that it's 0.20 joules for every gram you raise by degrees Celsius. Okay, so that's the specific heat of that problem. Sorry, the specific heat. And okay, let's look at problem number 2. So problem number 2, you start out with a mass of 45 grams. Okay, and so this is lead. It's cooled from 38 degrees Celsius to 20 degrees Celsius. And the specific heat of lead is 0.13 joules per gram degree Celsius. So you have a 45 degree mass. The delta T is 20 minus 38 degrees Celsius. And the specific heat was says 0.13 joules over gram degree Celsius. And so what I did is I rearranged it so that we have Q right, equals 0.13 joules per gram degree Celsius. So let's write this out. So Q equals 0.13 joules per gram degree Celsius. And our grams are 45 grams. So what I'm doing here is the G for grams. I'm giving the value here, and then degrees Celsius. So that's the change. So 20 minus 38, right, is our delta T. 20 degrees Celsius, which is our final, minus the initial. And so we're gonna, because we're taking more, we're subtracting 38 from 20, we're gonna have a negative number. So the delta T is minus 18 degrees Celsius. In other words, the temperature went down 18 degrees. So this C temperature change is going to be negative 18 degrees Celsius. Okay, and that's what I wrote over here. Okay, and then Q equals 0.13 joules over 45 grams degrees Celsius. Now, let me, I gotta write this out, and I'm gonna stop for a minute and erase this. And so it is, I wrote this out. So these here, I took these out and I actually wrote it out so it's easier to see. So one of the things you want to be aware of is, well, I just saw units cancel out in the problem over here. So if you look, you'll see grams up here and grams down here. So the grams are in the numerator and denominator, so they can cancel out. And then you see degrees Celsius here, over here, and degrees Celsius over here. They can also cancel out. And then I'm left with just joules, which is what I want, because it's asking how much heat, and heat is measured in joules. All right, and then when I multiply 0.13 times 45 times negative 18, what do I get? I get negative 105. So negative 105.3 joules. Okay. And then I'm going to talk about precision, and then I'm going to stop this part. And I'll make another one for talking about significant figures. Okay, so we talked about specific heat. Now, something I think a takeaway that I would like you to get from this, talking about specific heat, is that what is relevant to living things, including human beings, is that we're made up mostly of water. And it takes a lot of energy to raise the temperature of water. As a matter of fact, it takes 1 calorie to raise 1 gram of water by 1 degree Celsius. So it's a lot of energy that's required. Now, why is that important? Human beings are mostly made up of water. As a consequence of that, it actually means that we hold a lot of heat in our body because of the liquid. This is also relevant in the world that we live in, because the earth is covered mostly with water. So it actually takes a lot of energy in joules to raise the temperature of water. And also when water cools, it releases that energy. And because the planet is covered with so much water, that helps moderate the temperature of the planet. If there was no water on the planet's surface, our temperatures would be extreme from hot to cold, because the amount of energy that we require to raise the temperature is less. But then when you take the sun away, There's not as much heat energy stored on the surface of the earth. Water stores a lot of energy, so at night the water gives off a lot of heat and it helps moderate, in particular, coastal areas. And that's why you find coastal areas are milder in the winter and cooler in the summer. Okay, now accuracy and precision. So we're gonna this in this part. That's the last one I'm going to talk about. Accuracy describes the closeness of a measurement to a true or accepted value if the quantity is measured. In the measured quantity. Precision describes the agreement or closeness among numerical values to a set of measurements of the same quantity made at the same time. Now, what does that mean? Okay, let's say you measure a box. And I'm going to put on the scale. All right, this is our scale. And let's say that you take a measurement and it says it's 25 pounds. Accuracy would say, well, if the scale is saying this box weighs 25 pounds, how close is it to the true value of the weight of this box? In other words, if this box is only 20 pounds, that means it's not this is not a very accurate measurement. So if this is our scale here, right, the scale says 25 pounds, the box is actually 20 pounds, it's not very accurate. However, if that scale, instead of saying 25 pounds, it said 20 pounds, then it's very accurate. The scale is very accurate. Now, what is the difference between accuracy and precision? Well, if I make multiple measurements of the weight of this box, okay, let's say that I make 5 measurements. And if I make those measurements, and my first measurement is 21 pounds, my second measurement is 20 pounds, and my third measurement is 21 pounds, my fourth is 20 pounds, and my fifth is also 20 pounds. Okay, so now I'm going to repeat the measurements. Let's say I have someone else take the measurements with the same scale. And this time I make the measurement, I get 21 pounds, then 30 pounds, 24 pounds, 28 pounds, and 35 pounds. So if you look, this one here, right? These measurements are very close together. There's not much difference between them. We would say this is very precise. Measurements, however, can be precise and inaccurate. Okay? These measurements over here that were taken, these are all over the place. We would say these are not very precise. Some of them are accurate, but they're not very precise. But again, measurements can be precise and inaccurate. Oftentimes, we'll use a bullseye to represent accuracy and precision. If you took chemistry and they talked about it in high school, you probably were shown a bullseye. Okay, and so if I drew a bullseye, let's say it's like this. And I don't know how many rings are an actual bullseye. And then I'm going to use stars to show my measurements. My darts I'm throwing at. So one lands here, another one lands here, 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 and here. So what I'm trying to do is hit the bullseye, but I have them all over the place. I would say these are imprecise dart locations that they land. And they're inaccurate because I want to get them here in the center, but I don't have them in the center. Now, if I repeat this, all right, let's erase these. Erase this one here, that one there, and that one there, and I'm going to try again. And now I get them like this. They're all here. These are very close together, relatively speaking. So as we would say that these are precise. However, they're not near the bullseye, so they're precise, but they're not accurate. However, if I do repeat this again and I get a whole bunch of them here, all here in the center, these, because they're very close together, are precise, but because they're all hit the bullseye or close to the bullseye, these are very accurate. Okay? So that's accuracy and precision. Why are accuracy and precision important? In science, when we make measurements, we are talk about, excuse me, how accurate the measurements are and how precise they are. Precision really is dependent upon the methodology that a person is using to make a measurement. So if they're making measurements in a prescribed way, in other words, they're making measurements exactly the same method of doing it each time, you should get precise measurements. Accuracy is talking about, well, if I make those measurements, how close are they to actually what the value is for whatever it is I'm measuring? All right. All right. And so this is the end of Unit 3, and I'll do a Unit 4 for the remainder of this unit. Sorry, a Part 4 of the remainder of this unit.